Okay, here we go. Okay, so we are on chapter 9 today. And as I mentioned, chapter 9 is a pretty short chapter. And it's mostly on this concept of hypothesis testing. Okay, so before I get there, though, we did leave off on the last chapter, and I just updated the due dates for the last chapter. I did say don't do the stratified part yet, and so maybe we should talk about that first and then do this, because we're talking about making estimates, point estimates of the mean in a confidence interval, estimates of a proportion with a confidence interval, and estimates of a total in a confidence interval. So yeah, let's do that. Let's do that first.
Are we not going to use Jupyter anymore for the PowerPoints?
I don't know. I mean,
it doesn't really matter to me.
Okay.
I was just curious because I didn't notice anymore.
Yeah.
After 5.
It seemed like there was some. Well, okay. So the purpose of this course is the purpose of like any teaching is to like help people understand a concept, and then sometimes like teach how to do it. And this isn't necessarily like, I do want to grow this into a course where we could be using Python a lot, but it seems like there was some level of confusion in terms of I can't do this in Python, so therefore I can't do it. That's not what I was trying to do. The point of bringing up the Python was to show one way of doing that, to show one way of getting it done, and
just alternative ways of doing stuff like you do it through Excel. You can also
right.
do it through there.
And there isn't enough time to show every single way that something can be done. Right? And so, yeah, I mean, there's some value, I think, in doing it in Excel, because you have to think about every step, like, what am I doing next? What am I doing next? And you do in Python as well, but I will admit, even though it's a fairly high-level programming language, there is still some, like, okay, well, how do I actually program this into it? So, yeah, I gave up. I mean, I did do an example in Python because it was impossible to do in Excel 2 weeks ago. And that was when we talked about the central limit theorem, basically sampling from that distribution thousands of times in order to show the mean. I mean, I would have had to have like 1,000 different Excel spreadsheets and generate numbers. It would have taken a long time. So that's why I did that in Python. There wasn't anything in that Python to help you solve a problem. It was just that case. I was using Python to help. I was using a Python example to help you understand the central limit theorem, which basically is that. Well, I mean, maybe somebody wants to state this, but what is the main thrust behind the central limit theorem? Like, what is it saying? Anybody? So it's that all right, so what's a population? When I say I'm going to find out what the average income of Lamar County is, a population, it's important that we understand that concept, is the people that live in Lamar County for that particular question. Okay. A sample is a selection of those people, but only those people. We talked a lot about sampling. I won't go into everything we talked about sampling, but remember, random's the best, blah, blah, blah. So the central limit theorem says that when we have a population, it doesn't matter how a particular statistic is distributed in that population, the income, the people's heights, whatever. Whatever that distribution is, if we take a sample and compute the mean of that sample, we'll get a number. And let's say we did that 10, 15, 20, 30, 40, 100 times. There would be a distribution of those sample means. And those sample means will be normally distributed, and the mean of those sample means will be the population mean, is the best estimate of what the population mean is. And so the central limit theorem is what allows us to apply the normal distribution to a sample, even if the original sample wasn't normally distributed. I mean, even if the original population statistic wasn't normally distributed, because the sample mean as a statistic is normally distributed. The mean of the means is the means thing, and then that's one part that works really nicely in our favor. And the other part that works nicely in our favor is that the distribution of the sample means is normal, particularly as you get more and more of them. So the cutoff is about 30. So you get about 30, you'll get a pretty normal distribution. And that's why when we get more than 30, we can start just using the Z table rather than the T table. But that's only if you're using tables. If you're not using tables, you don't really have to use that rule, because if you're using Excel or Python, when you ask for the T distribution and you have more than about 30 samples, they're very, 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 very similar. They're almost the same. Okay. So yeah, that was a long way to answer that. Basically, that I kind of given up a little bit on doing everything basically building the class around the Jupyter notebooks, but I'm not giving up in the future with that. So let's talk about last week, particularly chapter 8. Now, I should have gone back and looked at the video because I did post it, but where did I tell you guys not to work past?
I think you said part 2, but I kind of got stuck on like after the first question or so.
Oh, okay. Okay. Well, we can go back that far, but I went back and read this really quick. So this is actually this book does have some, particularly the workbook, does have some mistakes. I don't know if you would call it problems. Sometimes I think the wording is a little bit confusing. And anyway, there's a mistake on this page, and that is that this says confidence interval estimation for random and stratified. This actually has nothing to do with stratified. This is just systematic. So it's random and systematic samples. And so for random and systematic samples, we did cover that material already. So you could do that part, or we could do it together. It's really just this part where it gets into truly a stratified sample, where we calculate, instead of being random, we got a certain number of apartments, a certain number of townhouses, and a certain number of residential condominiums. So if you do have your book, what I'm referring to is basically the difference between using the information that's contained in table 8.4 or the information that's tabled in 8.5. Because in 8.4, the math is a lot easier. It's a lot more simple than the stuff in 8.4. There's a lot of, n's and x's and the math might be harder, and I wanted to work through it together, do an example together in Excel for that particular one. Now, so this is the only time where you need to You need to do it here, and you'll need to do it here, because here we're talking about estimating this is the mean. We're talking about estimating the mean. Here we're talking about estimating the total water usage, and here we're talking about estimating the proportion of residents in favor of a proposed legislation. So we're doing all three of the there's part 1, part 2, and part 3 there in table 8.5. So we're doing all three of these. And unfortunately, there isn't a quick way to do this. Like, these all involve basically putting these turning these formulas into Excel, or just punching them out on your calculator. That's the only way to do this. Now, the formulas on the left are pretty quick to do in Excel, because the T table is already there. Yeah. But part 2 and part 3, even there, you're going to have to do some work to get those numbers. Part 1 on table 8.4 is really the only one that has a very quick solution in Excel. All right. Okay. So, Ashley, you mentioned that you might have a question up here. Is anybody else? Like, you're just talking the very beginning here?
I probably have some issues because I don't have the textbook in yet, so I was kind of going off of just what we talked about in class, but that might be what I was getting caught up on.
Okay, well, I mean, maybe I'll... What's that?
I was trying to pull it up so I could find where I left off that.
Yeah, and maybe I can come back, circle around to this. I did actually cover this a little bit in the video. What's going on here is that you're trying to get... Some of this has actually already been done in the worksheet. I got to bring the worksheet up anyway. This one.
Yeah, I think I got the number 3 is what I had the issue. I figured out 2.
Okay.
It was 3 is when I was really
Okay. All right. So that comes from this. That's a good question. So this is 123.16, and this, well, that's really all you need for this question. So the confidence intervals have been calculated. I mean, you could have calculated those too, but the confidence intervals have been calculated, right? And here's the sample average. So what you're going to do, and you can do this manually, or if you know how to do this in Excel, you could do it. What you need to find out is if 123.16, does it fall in this range or not? Does that make sense? That's what this question's asking. So what you're saying is, yeah, it does, yes, it does, yes, it does, yes, it does, and is there an example here where you see that it doesn't fall within that range? 123, that one almost doesn't. All of those look less than 123, right? Is it 123? 123.16. I don't see any that aren't. And then are any of these less than 123? All these are greater than 123. Are all these less than 123?
Row 19 is not.
Row 19. Yep. Okay, so that would be not. And then is there any others? So what this is asking is, what percentage of the samples and confidence intervals computed in the previous question actually contain the population mean? So this one does not contain the population mean. Okay, so let's say it's the only one. Well, how many were there? There were 51. Okay, so 1 out of 50. No, sorry, there weren't 51. There were just 50 because Yeah, because this is actually the number of how many there are. So 1 out of 50, what percent is that? I don't know if that's the right number. You'd have to go through and check, but let's just say it's 1 out of 50. What percentage is 1 out of 50?
Probably small.
What's that?
That's 2%?
Yeah, 2%, exactly. So if that was the answer, which I'm not sure that it is, I mean, are there 123.16? Oh, that's right on there. Ooh.
There was one more I saw, I think.
Okay. And then you could actually do it with all these, because theoretically these should also, with all of these should also 90% of those should also be in there. But anyway, what you're trying to say is what they're asking there is why doesn't it equal exactly 90%? Why is it that of all those samples that we collected, not that we collected, that somebody collected, why is it that it's, if we made a confidence interval that should include the real mean 90% of the time, how come it's 86% of the time sometimes and 87 others and 94 other times? And so that's what that question's asking. And don't overthink that question. It's like it's just like, I mean, is statistics. It's the samples are samples, and they're not always going to be. They're random. Okay, and the law of large numbers says that on average we should see 90% of the time that it falls within the that range, but in any given set of 50 samples, it may be a little bit off. Okay, but it's going to be close to that number. Do you see what I'm saying?
Yeah.
That's what that question's asking.
Okay, that makes more sense. I was confused. I thought I had to figure out for some kind of math for each one. That's what I was thinking about.
Yeah.
But I did read my notes that I do have a question on too. Is when you're figuring out the confidence interval, do you use the population standard deviation to figure that out?
If you have the population standard deviation, then you use it. If you don't, there's a formula for substituting in. So if you look at table 8.4, well, you don't have that, sorry. So let me bring up the slide from last week. Probably have it. Chapter 8. Oh, I was actually looking at, no, sorry. It's getting confused there. I thought maybe I was looking at the wrong week. Random or assisted, yeah, that's it. Okay. So if you don't have the population standard deviation, this is that's the number that you use to get. I mean, that's the value that you use to get it. Okay. So the best estimate of the mean, in other words, the best estimate of the population mean is equal to the sample mean, so we read this, plus or minus the confidence interval. And that is what you calculate. So the Z or T comes from the table, or Excel can provide that to you too. So you take that number and you multiply it by this value. And it's a function of the standard deviation. So it's the standard deviation squared divided by the number in the sample, and then it's it's multiplied by the total number of observations in the population minus n divided by n, the total number in the population.
Okay. Because I used that, the spreadsheet that you had created for us for a starter, and I used the population standard deviation. I was just making sure.
If the population standard deviation is provided, that's the best way to do it. Okay. But if the population standard deviation isn't provided, then you use that.
Okay.
So the this right here, n minus n, if you think about that, let's just say n is infinity, where we can assume n is infinity, then it doesn't really matter what little n is. You know, if n is a relatively small number compared to infinity, what does this equal? 1, right? So 1 times this number is going to equal that number. And this number is almost always going to be, this number right here is almost always going to be pretty close to 1, unless your population really does only have like 100 members and you sampled 30 of them. Well, if the population only has 100 members and you sampled 30 of them, then you should have a really good idea, a lot better idea about your confidence than if it was an infinite population. And so that's why you're multiplying a number less than 1 by your standard error, and so you're pulling that confidence interval in. But then you also have to ask the question, if there's only 100 people, why did I only ask 30 of them? Why didn't I just go ask all of them? Right? There's not that much more. So you might, the whole reason I'm saying this is that you might see where somebody in some other textbook or some other math just left this out, this n minus n divided by n, because that for a sufficiently large population, that term equals 1, or it's really, really, really close to 1. See what I'm saying?
Yeah.
So the basic, you know, if we can discount this, the basics is that you take the z or t value from the table for the appropriate confidence interval you want. So if it's a 95% confidence interval, then you take that value, which is for the z table, that'd be 1.96. So you take 1.96 and you multiply that by the square root of the standard deviation squared divided by the count. All right. So yeah, use sample variance. This is rare that we know the population variance.
Okay, that clears it up. I was just confused on what to plug in. I know how to work the formula for the most part. I was just a little mixed up.
Okay.
Okay,
Yep.
Thank you.
Sounds good. Yeah. All right, so let's go on. Is it raining out there? Wow. Those guys that are using my office this week, they were one of the things that they were hoping to do that came from different parts of the country, and they're working with the Naval Research Lab to basically design this system that will control drones and ingest data that they're receiving. So if they're tracking an object that they see moving around, it's a military application.
I hate that.
What's that?
I hate that.
Yeah. So they were, well, I mean, you're right. They could use it for all sorts of things, but it's yeah. But this is more for war fighting, not.
Okay.
I mean, whatever it could end up getting used for, right? But yeah. So this is for more for war fighting. But they were hoping to fly the drone, so hopefully it clears up.
Mississippi weather.
Yeah, Mississippi weather this time of year. It's crazy. Okay. All right. Let's go back here. All right. So here, what you're going to do here is is you're going to come up with this is a proportion. So this is, if you go back to chapter 7, I think I heard a few of you talking about how you did chapter 7's homework already. It wasn't super difficult. Nobody's done it? Yeah, you did it. So remember, did you pull up 7? So 7 had a bunch of maps. Oh, there it was. Okay, so 7 had a bunch of maps, and they looked like this. So and you actually have in real life, you probably wouldn't have this column. Like, we have a real estimate that the number of the DL category is only about 1% of this total area. Okay, DL is dune land. And then ED, in this case, is excessively drained. So you can see on the map where each of these are, okay? And we've sampled it 3 different ways. The dots represent samples. So what you need to do is, maybe you could do this with a partner or two, is to go through and for each one of these, count how many are in each category. So how many dots fall in each of these 1, 2, 3, 4, 5 categories. And if a dot falls outside of one of those areas, just don't count it or put it somewhere else. Okay? And then what you're going to do is there's 3 sets of them. There's a simple random, there's systematic, and so you're going to come up with an estimate for the proportion of each of these. So you might get a number that says 0.02 or something. How do you get that number anyway? How do you get that number? So if I count 20 dots and 2 of them are dune land, what's the proportion of ones that are dune land? 0.02, right? Oh, 20. Sorry, 20. Yeah. So it's what is it? 2 divided by 20 is what? 2 divided by 20. Yeah, 0.1. So it's way more, right? Anyway, I don't think it's going to be that, but you're going to fill this table out. And these numbers right here are actually the same numbers you're going to put right here, but the table isn't as big. So that for UL, and why is that? Why would I put the same numbers here that I put here for the point estimate?
Because you're estimating, it's not the raw data.
Yeah, so if we go to table 8.4 now I am in table 8.4, under 3, what it says is the best point estimate of the population is equal to the number divided by the total, which is what I just said, the 2 divided by 20. So the best estimate of the proportion is the actual proportion. How do we get the actual proportion? It's the number of observations in that class divided by the total number of observations.
I do have a quick question. When I was going through chapter 7, like I counted all the points, so I knew what to divide by, and there's 40 in each one. But when you're counting the points, like a huge chunks of them aren't landing in any of the samples. So do you still include those? Like,
That's a great question.
Still say divided by 40, or do you divide it by what hits the actual soil type?
That's a great question, and that brings up, that gets us to think about what our population is. Does our population include the water in this case? Like, are we concerned about water in our area? If we are, then we should include it. If we're not concerned about the water, In other words, if the water is not a part of our sampling frame, then we should exclude it. Okay? And since here there's no water category, oops, am I going here? Yeah, there. There's no water category here or here. Then what we're doing is saying that that's not of concern to us. So we're going to throw out any point that lands in the water, and that's acceptable. Like even if we sampled and our samples include something that we don't want to include in our population, we can throw those out. We can say those aren't included in ours, and our population is still random at that point.
So we're not going to divide by 40.
Right.
You're only going to divide by the points that actually hit soil. Because when I did it and I divided it all by 40, none of my proportions matched theirs. And I was like, I don't know if this is right or not. I mean, I know it won't match exactly, but some of them weren't even close.
Well, if you see, another clue is this says % land area. And so we're only concerned with the land. So yeah, divide these by the total number, not by the water. That's a great question. Okay? So you're going to get a number for each of these values. And then you're going to transfer those over to here. This column, and this column, the ones that say point estimate. Because the best estimate of the population proportion is the actual proportion. I mean the sample proportion. Okay? Then what you're going to do is you're going to plug that into the formula there for the confidence interval bound. That formula isn't extremely difficult. It's it's the little p is the proportion, and then the n is the number. In this case, the n is the total number of land points. Again, don't use all the points, just the land points. Right, and then big N. In this case, you could just go ahead and use the total area, like if you want to. But in doing so, that second term is going to go really, really close to 1. So you could just ignore it. It's going to give you almost the same result. Because you're going to have less than 40, and then your area is going to be something huge, some huge number. So, yeah. So you can see how the star at the bottom of the table says exclude the finite population correction from the confidence interval equations if n divided by n is less than 0.5. So you can exclude it. So really, you're just talking about that other part over there. So we could set that up. Does anybody? Let's just do one. Has anybody come up with the point estimate that you got for one of these three?
Oh, I do, but it's wrong.
Well, do you have the original numbers you used to calculate it? Do you know how many were water?
I don't know how many were water, but I know how many were in each of those categories.
Okay.
I counted them up.
Yep, count them up and tell me what the total is. So I'm going to open up a new sheet here.
The random sample is 26. Actually hit.
I'll put this in here so that you guys will have it. So I'll call this sheet proportion. What question is this on the homework? What's the number? Question number?
On chapter 7 or chapter 8? Because we're using chapter 7 stuff in chapter 8, correct?
Right, but we're answering chapter 8 right now.
Okay. I think it's like 5 or 6. It's on 5.
Proportion question, I'll say proportion question 5. Okay? And so the way I would set this up is I would just copy this table into there. UL, for the other things I said bad about this, that there's some errors in here. The good thing about this is that, for the most part, I think that they are good at setting up these tables in a way that you can easily transfer them to a software like Pandas or Excel. So here we're going to our point estimate, and then we've got our confidence interval. Confidence interval. Well, I'm just going to call that CI because I don't want that to be too big. Okay. All right, and then we're just going to take these two values and copy them across, and we're going to have 3 of those numbers, and we could put up here, this is random or simple random, simple Raber, that's me, random, and simple systematic, and then finally systematic aligned. Okay, I should have had that already typed up. All right, so we're going to do just this one. So what did you say was the total count in the simple random one, not including water?
26.
26. All right, 26. What did you say was the number that fell into UL?
There's an issue. There is no UL. It is either DL or UD. So that's a typo. I don't know which one it was.
Oh, so there's another error. So yeah, let's.
Go to chapter 7. You'll see that it's really not a UL.
Let's do UD. Yep. Let's do UD. Did you have a count for that?
Yeah, 10 hit on that.
10. Okay. So 10 divided by 26. I'm gonna change this to UD. All right. 10 divided by 26 is the point estimate, and that's actually pretty close to what they have as the percent, the raw data. Okay. All right, so let's calculate the confidence interval. And if we want to, not if we want to. Let's just throw out the finite population correction factor there because the population size is so big, and we've collected relatively few numbers. So we don't need to worry that our confidence interval is going to be too wide. Let's just make it, basically, the finite population correction factor narrows your confidence interval. It basically allows you to make a more precise estimate because you know so much about that small population. All right, but let's just ignore that. So the formula there is, I might actually insert one more table here. Line here. And we're just going to call this ST error, STE, because that way we can calculate this and then go look it up in the table and do the final estimate. Okay, so this is going to equal, it's the square root, let me get it on here so that I don't have to just tell you. Okay, it's this right here. We're going to ignore the finite population correction because we can. And so it's this term that we're doing. The square root of p times 1 minus p divided by n minus 1. So we're going to say it's going to equal the SQRT of p. What's p in this case? In this case, it doesn't mean like the
26.
Where'd you get 26 from? It's not 26.
The total points that were collected that were actually in our study area.
Okay, so that should be, the total number should be the denominator of that. if you look at the best point estimate is of P is equal to X divided by N. So it's the total number of it's the total number of that observation divided by the total number of observations. So this is P. It's the proportion. See what I'm saying? Okay. It's the proportion times 1 minus P. Now, order of operations says that it's going to do the multiplication before it does the subtraction. That's going to be a big problem because it's going to just equal 0 if I don't put a parenthesis around this. Okay. All right. And then I want to divide that by n minus 1. And I got to put another parenthesis here so that it doesn't do the division before it needs to. Okay. So I'm going to divide that by n minus 1. What is n minus 1? N is that number that you said. So there are 27 total points, you say?
26.
26. Okay. So it's 26 minus 1. And I'm going to put a parenthesis around that. And then a parenthesis around the entire thing. Going back to this one. Okay, so that's what that needs to be. So this is the formula that just implements this right here. That's the formula that implements that. And so you just need to make sure you get all those parentheses in the right places. But other than that, it's a pretty easy formula. Now, if we wanted to, we could put this number 26 somewhere in the table. Okay. That might be another line if we wanted to do it that way. It might be easier if you ever come back and do this homework later. So you could put up here, count. Let's just call this X because that's the count. So how many UDs did we say there were? 10. And then up right here, yeah, I'm going to put the total. It's 26, and I'm gonna if you label something like total like this, I'm just going to call it N. Then you can refer to it as such. So now I'm going to change my formula slightly here, so that this is B3 minus divided by N. Okay, it's X divided by N. Right. And then I can change this formula slightly so that this is N, and everything else can stay the same. So you might have to add another column, X right here. Insert X right here. And then what I might do just for clarity, let's put these guys around like that. So now I have, three distinct things. So I can put the count. The reason why this table probably didn't have not this table. This table probably not this table. This table probably didn't have those is because you're just taking them off of the other screen. But anyway. All right, so that is the standard error. With the standard error, we can calculate the confidence interval. Now, if we have more than 30 samples, we can use Z. Okay, but we don't. So let's show this again. So we should use we should use T. This doesn't say Z or T, but we should use the Z. All right. It's safe to always use T because T actually asks. T will actually ask for the number of samples anyway. Nope, that's not the right one. Okay. All right, so yeah, this is X, the degrees of freedom, which we'll actually explain better, I think today, if not today, next week. But it's just N. It's the reason why you include this is because it's the number of samples minus 1. Okay, so it's the number of samples minus 1, and then you say whether or not it's cumulative or not. Okay. If you notice that it returns the left-tailed student's t-distribution. Even if we used the so normal is the mean as well. I mean, sorry, it's going to ask for cumulative as well. Or sorry, my point is whether or not it's the. Yeah, it's, well, let's click on the help here, because I'm pretty sure it returns that as well. I think it's the left, the value for which you want the distribution. Let's see what we say. If we go t distribution, the x value, here we can hit the help on here too. So the numeric value at which to evaluate the distribution. Okay, that's the value This is going to give us the area under the curve, assuming, right, okay, so if we were to follow the book here, we'd need to go to the z distribution or the t distribution, and we need to look for it at, what did it ask for anyway in the homework? What's the 95% confidence interval? So at the 95% confidence interval, what is the value? 1 point. I mean.
You get that from the Z table, right?
Right. You get that from the Z table. And what you're looking for is, because you're looking at for 95% of the area. And in the table, it's actually giving you just from the right of that 0 mark over. This is what I did on the board last, not the board, the drawing last week. So if we want 95 to be left, what area under the curve are we looking for? Well, last week I said basically what you're going to do is take that number left is 2.5, right? And you're going to find that value, and then half of it and find that area under the curve. Okay. All right. Does that sound like a little bit of work? Well, the reason I'm showing you that is what we're actually getting here. Let's first do this with the normal distribution, okay? So the normal distribution, that function doesn't actually apply here. Yeah, it can apply. So the way that we can do this and make it work is that we can make the mean 1 and the standard deviation, the mean 0 and the standard deviation 1, and then we can get the value that we need, right? So x is the the estimate of where we want. Yeah, okay. The inverse is what we want. Okay, so the probability is what in this case? 95% confidence. We want the opposite of that. What's the opposite of 95%? 5. So 0.5 with a mean of 0 and a standard deviation of 1. Oh, then we need to say, oh, 0. Yeah. Did you see how that was 0 if I put 0.5? Because exactly half of that area is under the curve. Okay, so now we get 1.65. And we don't want just this. We want to actually multiply that by the standard error. So we add it to the standard error. Or no, multiply, right? Formula, yeah, it's multiply. Sorry. It's the formula that's at 8.3 at the bottom. It's this right here. We got this term. We're multiplying it by the z value that we just found right there. So we say this times this value, and that is the confidence interval. Now, why is it negative? Because in the book, the z-tables aren't ever negative. Oh, the formula?
Yeah.
Sure. Basically, this is the equivalent of looking it up in the tables. Okay. So let's do that in the table. So if we're looking for an area under the curve to be 0.05, then what we want to do on here is to actually find one that is 0.45 in the z-table book. Why? Well, because that is the A that's shown in the table. This is what the book looks like for you, those of you who don't have a book. This area is filled in, and it says A inside of it, right? Okay. And what we're looking for is what area. I know this area, okay? I know that area, and I want to find the line, this green line that goes like that. I want to find that green line. Where is that green line on the standard normal distribution? And all I know is this, but the table gives me a bunch of these values. I know that this entire area, the black shaded area and the red shaded area, I know is equal to 0.5. And so to find this area that is the opposite of that, the complement of that really, what I need to do is take this area and subtract it from 0.5. And I know that this area right here is half of 0.5. So that's why I need to say 0.05 divided by 2 minus 0.5 is 0.475. And that's why I need to look in the table, find 0.475, and it's if I look at it, I'll get a value of 1.96, which is given in other places in the book as the value that I need, 1.96. Now, if I take this off here, I should be getting, if I'm not getting 1.96, I should be worried. Oh, 1.64. Yeah, I'm worried because I messed up, because here the probability I'm saying is 0.5, and I actually need this to be 0.25 times this. That's why it's always important to think about whether or not it's, if I'm just concerned with one of the tails or both of the tails. The total of both of the tails is 0.25. The total, because the total of the whole thing is 1. The total area that I want to build the confidence interval for is 0.5 or 0.05. And so half goes into each tail. Right? So this is the confidence, confidence interval value. What I really want to do probably is say that I could either do this. What's 1 minus 0.25? What's that?
I'm sorry, I misheard it. That's a dumb answer.
1 minus, there we go, I can just do that. See how that number and that number are very similar? 0.1907. So 1 minus 0.1907. Why are those almost the same number? One's the opposite of the other in terms of, one's negative, one's positive. It's because I'm going on either side of that distribution. So now I have a positive value there. And so the confidence interval, this is the base, but it's basically this number plus or minus that number. That's what I want. And I could insert, put that, wonder if I clear. There's no borders. No border. And then rebuild this as thick outside borders. Okay. So confidence interval lower and upper. So technically this would be plus what? The point estimate. And then I could just take this over here. It's still the standard error. It's this, but I'd say minus that. Okay. Something messed up there. Okay, so this is the standard error times plus the point estimate. Standard error that number isn't right. Oh, sorry. That's the standard error. There we go. Minus that. Minus the point estimate. All right, well, this is definitely the right number, the upper, because I'm adding, what I'm trying to do, it might just be easier to do this. So this is the confidence interval. that's going to equal this. Oops. And then that is going to equal this plus this. And then this is going to equal this minus this. So that's the confidence interval. That's a 95% confidence interval. Pretty wide, right? Like, so 95% of the time that my estimate of the true population standard deviation, the true population proportion is 38%, but it could, 95% of the time, it should fall anywhere between 19% and 57%. That's the way that I would read that. All right. So with this, you could continue on with the homework. You could go fill these numbers out, and you'll get a number, a different set of numbers for each of these. Okay. Don't know why that. There we go. Nope. That one's not included in my. All right. So you'll fill this out, and you should find that most of the time the true mean. By the way, where is the true mean? Not the true mean. The true proportion. Where is that? It is in the worksheets. All right, it's right. It's right here. So this is that's the true population proportion. So obviously this one falls in the right place. Okay. I messed up what page I'm on there. All right. So that is the right number for that. See how I just did that as this is this formula right here, except for the z part. And so the trick is finding z. How do I find z? And that's, so I actually just have 1.65 and 1.96 memorized as the numbers for those. And you'll see that in literature as well. Yep. Those are pretty common. 1.65 would be 90, 1.96 would be 95, and 2.58 is 99, and those are the three most common ones that I see. Okay, so I'm going to save this, and I'll push it up to GitHub, and you can have this to fill out the rest of this table for your homework. All right. Okay, so let's look. Yeah, it does say UD here. It's UD. Okay. All right, let's look at this one. All right, so here in each of these three, we're going to utilize the formulas in 8.5 to answer each of these three questions. Okay, 1, 2, 3. Average, total, and then proportion. Proportion doesn't have anything to do with water, but the other two do have questions with with the water. So what I'm going to do this question is I'm going to open up the homework example as well, and maybe I'll make a table inside. Well, actually, here I'll just put it at the bottom of this table. Okay. So although I'm going to be drawing some information from this table, I'm going to put my work table in this table because it's already pretty small. Okay, and we do need some of the numbers from this table to answer the question. Okay, so my work table here is going to look like the work table in the book. So I'm just going to copy these three down here and do that, and then I'll say totals, and then best point estimate. Oop, that should be up here. Confidence interval. And really, we can do a lot of the math will be the same. So here you're given one table here, and you're given another table here, but here you're trying to find the average water usage, and here you're trying to find the total water usage. So we could just come down here and say average and totals, or we could reverse those because average is the one you're going to do first. Okay. And then we could put in the rest of this table. So population size, and then sample size. Okay. All right. So both of these have the same information in the top part of the table. Okay. So this first question, they sampled 40 residents. That's this table right here, 40 residents. So what's the population size for apartments? Is that given anywhere? It's not written in the text of the homework, but it is on this sheet. What's the population, the actual population of apartments in this town? How many apartments is another way to say that? Where is it on that sheet? Yep. C2 there. So there's 100. So we could just type that in, 100, 196, and 395. So that's the total number of properties in the city. I mean, that's a small city, right? It's only got 100 apartments, 196 residential condominiums, and 395 townhouses. But that's the way it is. Okay. So how do we figure out how big our sample size is? That information's on this chart, on this one. So how many apartments are there that were sampled? Because this is the list of the sampled places.
Take the proportion and multiply it by the total, right?
I'm sorry?
Found on one of the spreadsheets that showed like the total count of 100 and then next to it was a proportion.
But I'm just interested in how many are in our sample. How many apartments are in this? This is our sample right here. I'm telling you, this is the sample data. How many apartments are there? Yeah, there's 7. now we put that number over, sorry, I'm in the wrong one. Go back over here. The sample size is 7. We sampled 7 apartments. How many residential condominiums did we sample? Sorry. It's right here. So how many are there? 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I got 14. Okay. And then finally, how many townhouses did we sample? I keep going back and forth, but they're on the same one. What's that? That sounds reasonable to me. I mean, the nice thing about Excel is that it's not super vital that we get the exact right number right now, because if we set it up in a work table, we can change that number later. And then all of our other numbers, they'll cascade onto it. So let's just put 26 for right now. Okay, that sounds good. All right, so now we have our sample size for each of those. So now we can calculate our sample mean and our sample standard deviation. Let's go back to our sample sheet. What is the sample mean for apartments in terms of, I'll scroll up, in terms of, what did I just do? It looked like something disappeared, hopefully not. So in terms of water usage, because that's the variable we're looking at, the average water usage per household. So what is the average water usage? How do I calculate that for apartments? I mean, you don't have to calculate it. Just tell me how I would do that, and I'll do it in Excel.
Add all this together and then divide by how many there are.
Yeah, add all the water usage up. It's in thousands of gallons. So this apartment uses 6,000 gallons. So what we can do, we can go between sheets. So I can say equals, and then I can go back over to the water meters. Oh, sorry, I need to actually finish the formula. Say equals average, and then go back over there and just make sure I just highlight just those 7, and then hit enter. So that's the average water usage for residential condominiums. And then I do that again. Average all the way down, residential condominiums, bam. Average, oh, yeah, did I do that right? Okay, and then the townhouses.
It lets you go back from one sheet to another. I've never done it. You just literally just go back.
Yeah, you press, as soon as you press parentheses, then you can switch over to another sheet.
Okay.
Highlight what you want, press enter, and it'll go back.
The other sheet. Okay.
Yep, so that's what I did there. Cool. So this is pulling from another sheet, right? We can do the sample standard deviation the same way, right? We could. I'm just gonna copy this formula over and put it in there, and then change the word average to standard deviation. The sample standard deviation is right there. So estimate standard deviation based on the samples.
So it's standard deviation S.
Dot S, yeah. The difference is that it's dividing it by n or n minus 1. So it's basically punishing you for having a small sample size. Is what that does. So, and it calculates that for you. So I'm gonna pull that in. Whoops. I didn't finish typing standard div. I have to like click on it. There we go. All right. And then I can do the same thing. I don't know if there's an easier way to do this. Like maybe a fill down would work, but I'm not sure it would get the right. I'm not sure it would figure everything out. Actually, I do know. of a way I could do it, but it might be almost as hard. So one thing I could do is just pull this. Well, I could put little. If you put a $sign, then when you do a fill over, it won't change it. So if you put a $sign in front of each of those, and then you pull this over, see how it didn't like move to the next column like it normally would. A $sign in front of it. But it's still average, so I still have to go change it to STD. Nope, not standard dev S. Okay. So those are the sample standard deviations. Those are the sample means. Okay. Now we have all the information. We've compiled all the information that we need to come up with these numbers. But it's not as straightforward now that the best point estimate, we could actually calculate, we have the best point estimate of each category. In other words, we know the best point estimate for apartments. That's it, because we're assuming that this is a random sample of apartments. So the best point estimate of the average water usage for apartments is 95.57. It's kind of interesting. I hope we calculated that right, but I wonder why apartments are using so much water compared to everybody else. It's pretty crazy. Let's make sure I got the right value, right? Yeah. That says B2 through...
I think there's 8 apartments.
I think there's 8 apartments?
Yeah.
Is there another one?
Maybe not.
But there are some really high ones in there.
Yeah.
Yeah, so... maybe they have like really...
That's
nice
weird,
apartments
yeah.
in this town or something, but in any case, it's a weird house, a weird place. So, okay. All right, so this is a proportional stratified sample of homes based on dwelling type, okay? So, by the way, when it says we have the luxury of actually knowing the population values for water usage, that's what's in this. This is the actual. This is the actual number. This is the actual amount of water usage. Could we calculate an average for that? I think that would just be, equals this. Sorry, this divided by this. So that's a lot higher. Oh, yeah, that's in thousands of gallons. What's that? Yeah, so our numbers are going to be off for sure already. I know that, but in any case, let's come up with that. So it's interesting. These two numbers look way more like the real numbers. But this one does not. Okay, so let's come up with these numbers right here. So what's the best point estimate for the average? Well, if you look at that formula, and I'll bring it up here too, it's kind of a big formula. This is the formula that we're talking about. Yep. Right there. Let's make sure I type this in right. 1 over n. Actually, this looks like there's a problem. Yeah. Okay. So anyway, that looks like the formula, but I left out the x bar term when I typed it up here. But Anyway, the correct formula is in your book in table 8.5. It should look like this right there. All right, so all right, let's look at how we calculate that best. Oh wait, no, sorry. These are two different formulas. This is the formula for the best point estimate that we're on, so it does require that x bar, just like that. And then this is the formula for the standard error, which makes sense that the standard error formula doesn't include the mean, because it's just a measure of the spread. Okay. So anyway, we're first going to calculate this. So let's look at this. How do we would interpret that? Well, this is basically saying 1 divided by the total population value. So this is the count of all of the count. Wait a second. And m is the number of strata, so we're going to do this for each one. So it's the mean is going to be equal to 1 divided by the population of the strata times that number times the individual mean. Okay. Let's see. Yep. Okay. So in our case, big N is equal to this number, the total in that, the population parameter for that strata. These are called, the general term for these is the strata, or the stratum, the singular, or stratum singular, plural, strata singular. So this is the big N, that's the little n. So what we're trying to do is replicate this formula to come up with that number. So, yep, all right. So this term gets multiplied by everything. So we can just go ahead and figure out that term for each one. Okay? That would be 1 divided by this equals 1 divided by this times this. And fill that down. So that's this term. Now we need to find this term, which is the number times the x bar. So here is the x bar. The sample mean is another way to say that, a better way to say that, times the population in the sample. See how that's this times this? There is a work table that's similar to this. On table 8.8 is showing the a work table that does this. Right, so we're kind of doing, oh no, that's difference in proportion. So it would be like, trying to find sample mean. Yeah, it'd be like table 8.6. All right, so we have this column. This is actually the overall. I didn't need this column, sorry. So we have this column, which is the sum of all of those numbers added together. It's basically this part of the equation. Okay, and this part of the equation we only do once. So let's make the best point estimate equal to the sum of this column times, I'm going to put a parenthesis, 1 divided by n, which is the total number in all the strata. The big N, not n sub whatever, just the total number in all the strata, which is 691. So I can just put that right there. That number's not right. Sample size, standard deviation. X bar times 480. X bar this times that plus this times that plus that times that. Yeah, that should. Well, that number does not seem to be the correct number. Because this should be an estimate of the average population. I mean, sorry, the population standard. I mean, so the population mean, and that number is not correct. I mean, there's no way that that's correct based on these. Oh, I just saw my error, right? No, that's sample mean. Sample mean times the n. Oh, I know what I did. There we go. All right. Yep, that's right. Okay. So it's the population count, not the sample count. It's big N. So we got that. That's the correct number. Oh, but we have to do one other thing, because this is definitely a yeah. So we have to calculate the confidence interval. So the confidence interval around X is that other formula. And these do have big N's and little n's. So remember, the big N is the population, the little n is the standard deviation. I mean, the big N is this is little n, this is big N. And that's what I did. That was my mistake here. All right, let's see if it would be easier to break this up. I think it would. I'm going to make one called FPC. I'll just put it right here. Okay, so the FPC is the finite population correction factor, and that's going to equal, actually, I'm going to put that over off to the side over here. Let's label this column while we're at it. This is going to be X, or sample mean times pop size. Okay. I'm going to overwrite that. I'm not overwrite that column, but it'll be behind there. Okay, so the finite population correction factor for each of these is going to equal the the total population count minus the sample size count divided by the population size. And then we need to fill that down. And you see those numbers are still pretty close to 1, but they're enough off that we should use them. Okay. We don't have that many observations. So we can make better estimates of our confidence interval. Okay, so that's the finite population correction factor. And then we've already got, I think we have the rest of everything that we need here. Well, we could come up with a term, because we have to do this for each one. See how the middle term here is the standard deviation squared divided by the little n. This is the little n. So we could make I'm just going to call this term 2. I think sometimes this is better than making big old formulas in Excel. So term 2 is the standard deviation squared, so sample standard deviation, times the sample standard deviation divided by little n, which is this guy. And fill that down. Okay. All right, so now we just need to multiply. So to get our sum, we need to multiply n squared times the number the second term we just calculated, times the finite population factor. So we'll call this sum values. And it's going to equal this times this, because that's the first term here. And then multiply that by the second term, and multiply that by the finite population correction factor. And then fill that down. All right. So now we have all those numbers. We need to add them up and do the 1 over n squared. So that's this number squared. So our confidence interval, let's do one more. Let's call this, this will be the standard error. So that's going to equal the sum of these guys. The sum of those, see that's this term, times 1 over n squared. Divided by this times this, whoops, C5 times C5. I'm going to put C5 times C5 in parentheses because it needs to be done first. And actually, I'm going to put all this in parentheses because it needs to be done first. Oh, and then all of this needs to be square rooted. SQRT. .383565. All right. Now that's the number that I multiply by what did we say to do this time in the homework? Which confidence? 90% confidence interval. So if it's a 90% confidence interval, there's 10% total left, 5% on each side. So here we really are going to do that. We're not going to do 1.96. We're going to do 1.65. So we just multiply this. This is equal to 1.65. And we could get 1.65 by doing the normal inverse and saying 0.5 or 0.05, mean of 0, standard deviation 1. That would give us 1.65. It's about 1.65. And multiply that by our standard error. Okay. So that's our confidence interval. So it's plus or minus this value. So if we wanted to say what's the best point estimate for the average water use for all the places in our city, what would we say? 90% of the time it falls between what and what? If this is the confidence interval, 8.85, and that's the point estimate, what do we do with the confidence interval to get the, sorry, that's the base confidence interval. What do we get to get the actual confidence interval? What do we do with this number to make an actual interval from this value to this value? What do we do?
Turn it positive.
Well, we do have to turn it positive, but then we also need it negative too, really. Why? Because it's plus or minus this value.
Is it just supposed to be on opposite sides of the, is that what you're saying? Like one on one side of the distribution?
Yeah, so another way to think about this, let me bring up, see if it's here. Yeah, okay. One way to think about this is that when I did this part of the formula here, the normal dot in 0.50, what I did was I figured out if the mean was 0 and the standard deviation was 1, I figured out what that was and what that was. Really, I only figured out one or the other, and it was this one that I figured out. It was 1.65. So then I said, but my mean isn't 1.65. My mean is 48.04. And my standard deviation isn't 1. My standard deviation, or my standard error, is 5.383. So I need to multiply the distance from the mean that I want in the standard normal distribution, which is just 1 is 1 standard deviation away from the mean. Another way to think about this is 1.65 is 1.65 standard deviations away from the mean. All I'm doing is expressing how far away I am in terms of standard deviations. Then I can multiply my standard error by that number, and I find out instead of a mean being 0, what if the mean was 48 and the standard deviation instead of being 1 is 5.85, whatever. And so I multiply, in order to scale it, all I'm doing is multiplying this distance by my standard error that I figured out, multiply that value out, and I find out where I really should be in order to capture 98% of those sample means. Or 90% of those sample means, sorry, 90%. So that's why this confidence interval is, I'm recentering it from 0 to 48 by adding and subtracting this. But I also need to scale it. It's not just 1 anymore. Standard normal distribution, the standard deviation is 1. I need to rescale it up to 5.35. And so I'm not going 1 standard deviation, well 1.65 standard deviations. And then, so this is plus or minus this. So I'm having a hard time coming up with this term, what a term for that, but this is the basis for my confidence interval. It's plus or minus that value. And there's the minus value. If I wanted this, I could just go like this, right? Now I get positive number. Because, do you see that the difference between putting 0.95 and 95 is the difference between getting this number and getting that number. And they're just standard deviations away from the mean. Getting this number versus getting that number. They're standard deviations away from the mean. When the idealized is 0, 1. I mean, sorry, 1 and -1. This would be -1. Right, so that's the best point estimate. This is like the confidence interval base or something. I don't know what to call it. And then let's say upper, lower would just be equals this plus this equals this minus this. So that's not the way we, I mean, the long way to say what those numbers represent is that 95% of the time, 90% of the time, the true average water usage for our city should be within that range, given the sampling design that we created. So the way to shorten that down is that we're 90% confident, 90% confident that the true population, the true population average water usage falls in that range. We're 95% confident that it does. So in other words, if we proclaim that it is between that range, what we're doing is saying that we're okay with making a mistake 1 out of every 10 times. So if you wanted to not make a mistake that often, if you wanted to increase the probability that you didn't make an error, then you could change this confidence interval base to use, 995 would be a lot more. That would be 1% chance, a 90% confidence interval. But you see how much wider our confidence interval has to be to do that. It went up a lot. So let's change this back to 0.95. So it might seem weird that we're using 0.95 for a 90% confidence interval. But why are we doing that? Well, it's because it's considering both tails. Later, in fact, if we get to it, hopefully we get to it today, but maybe we won't get to it. In chapter 9, we're going to say, okay, well, what is the probability that the true sample mean is above the true population mean is above this sample mean? Well, that only involves looking one direction. So there are times when we only want 1/2 of the curve, but this isn't one of them. Okay, so I did warn you that it might seem overwhelming, but this isn't a big, huge part of the course. There is a lot of math to calculate these stratified samples, okay? There just is. There's a ton of math, and we did it, but we did it once, okay? There actually are cases where this does come into play, and where it comes into play the most in my research is that I'm often involved in calculating the average, the average error that a map has in it. And so if you go out and take samples, like if I make a map and I proclaim this is a land cover map of a certain area, and I go out and I want to find out how accurate the map is, if I go to 30 of each land cover type and I determine the accuracy, I have to use this exact method to come up with the average accuracy for the map. Because there may be only 30% forested and 10% urban. But if I got 30 of each sample, then I'm not going to make the correct thing if I use the table 8.7. I need to use table 8.8's math to do that. Okay, so that's the time when it works. That's the time when this applies to what I'm doing. Now, if you truly did do a random sample, then you could use table 8.8 math, and then it's a lot easier. It's there's still some questions, and I mean, there's still have to know how to do it, but it's a lot easier. Okay, so now you just have to do this again for totals, and there is a work table. Oh, sorry, I was coding the wrong ones in my just now. I was saying 8.4 versus 8.5. There is a work table for each of these. So 8.6 is the work table for part 1 of 8.5, which I kind of used as we went along. 8.7 is the work table for part 2 of 8.5, which is the next thing that you would do right here. I wonder, okay, so it's actually interesting that we could do that first part together, and then we'll take a break. So the best point estimate for the total, you could see, is almost the same as the best point estimate for the mean. The only difference is that 1 times n term. In other words, you're not dividing everything by the total number. So this right here, you're just not doing this part. So we could just take this, copy, and paste that right there. It's the sum of these values. In other words, what were these? Well, these were the sample mean times the population size. So, in other words, what we're doing is saying that it's the average amount by population, but we're weighting each of those, right? Another way to think about that is these sample means get weighted by how many there were in the population. I mean, it's the exact same formula for weighted mean. So this is weighting each one of those, and then we're just adding all those numbers up, those weights up, to get the total. So this is an estimate of the total water usage in this town. And we can look at the number, and we're off by a lot. But we can see we would have been off by a lot because that number, this number is so far off the others. I wonder if there's a mistype in there. Does anybody have another version, or is everybody using my version? Anyway, I wouldn't put it past it to just have a missed number up there. What would happen if we... Ooh, that is pretty close. You know, so there might be an extra digit. See what I'm saying?
Yeah.
So, because that is not too far off of that. I'm thinking that's what happened in when they dispersed the water. That number is just off. See what I'm saying? By one number. I think somebody just fat fingered one of the numbers. Because that would be reasonable. But I could see if there's an update. Okay. But in any case, that's the best point estimate. And that's easy. And then how do we do the confidence interval? Well, the confidence interval is right below it. So first we need to calculate the standard error. And the standard error is we've still got almost the exact same terms. The only thing that we're not doing is that 1 divided by n over 2. So we still got term 2. We still got the finite population factor. It's just that now we're doing the sum of the we're doing the sum of all of the n's squared. Sum of all of them squared, rather than just, oh, that's still there too. In fact, the only thing we're not doing is that 1 divided by n squared. So we could, see this, no, sorry, the standard error, yeah. So basically the only thing we're not doing is this part of the thing again, because we're still doing everything else. Yep. So we could just copy this, put it right here, and this time remove all of this. Take out the multiplying sign. think that's going to be right. The sum of those, what were those? Those were that squared, that's correct, times term 2, that's what I'm calling it. It's the standard deviation divided by n, times 3, got it. Whoops. Escape out of there. Okay, so that's the standard error. And then let's take a break there. And you could figure out with this, you could figure out what the confidence interval base should be. Remember, it's going to be this times, it's still going to be the same. All we're doing is scaling it up. So it's still going to be times the z value. Okay. All right. Now, in that formula, by the way, this is where we are now. Yeah. In this formula, when we say t plus or minus z, t here doesn't represent the t table. This is still the only, the standard error that you're going to get out of the z table. Which, what is it? It's not going to change. So what is it for 90% confidence interval? 1.65. So it's 1.65 times this number we just calculated. So you could just take that value, multiply it by 1.65, and then what do you do to get these two numbers? Once you have that number, that confidence interval base. Once I have something here, how do we get these two numbers? Well, that's what plus or minus is. All right, let's go ahead and take a break, because I need to take a break. What do you want me to leave it on?
Kind of like your summary values cell I in.
This one?
Yes.
Okay. And then all of this, I'll re-upload, so we'll have it. Because I'm not going to mess up too much by putting this. I'm not going to mess anything up, especially since we're not using Python anymore. I'm not going to mess too much up by uploading this to the. This will fit into Python pretty well. Okay. So the only thing left here is you've got these proportion of totals. So right now we're almost done with this. Yeah, we're almost done with this question and this question because the work tables really are almost the same. The only difference is this bottom part. Okay, so the only thing left is this table right here, and you're going to be doing it a little bit differently. It's the last set of numbers, but you're still just going to come up with a best point estimate and then a confidence interval. And again, it's probably the largest formula that you'll do for this class is this. So like in some ways, once you do this, you're on the top of the mountain of formulas that you have to calculate. Okay. So there are a lot of cases where you don't need to worry about stratified sampling. But there are some cases where stratified sampling happens, and so you need to know about it. All right, so let's take a break and come back in about 15 minutes.
When is our spring break? Oh shit.